In the country of United States of Heightlandia, the height measurements of 10-year-old children are approximately normally distributed, with a mean of 53.3 inches and a standard deviation of 4.4 inches. What is the probability that the height of a randomly chosen child is between 51.2 and 56 inches? Do not round until you get your final answer, and then round to 3 decimal places. The first thing, as always, is to sketch the bell curve whenever you read that the distribution is normal or even approximately normal. Make the bell curve, figure out where your mean is. 53.3 inches is in the center, and that means that with a standard deviation of 4.4, these two values fall about here and here around the mean. So we have a shaded region in between that represents the probability that a randomly chosen child will have a height in this range. Now to find the answer, we can put in our mean of 53.3 inches, our standard deviation of 4.4 inches, and we're going to need two x values. So the first x value is 51.2, and that has a z-score of this x value minus, this x value minus this mean, and you can make that an absolute reference, divided by the standard deviation, make that an absolute reference also. And then the area will be norm.distribution, norm.dist, the x value, comma, the mean, absolute value, comma, standard deviation, absolute value, and 1 for cumulative. The area to the right of that would be 1 minus the left area. So we'll go ahead and copy these formulas down and enter the other value, which is 56 inches. Now that I have my areas, the left areas here, I can find the area between by taking the larger left area minus the smaller left area. So the larger left area would be the one to the left of 56 here, all the way back. So that would be this one. Minus the smaller left area, so I'll look at the smaller left area here, would be from 51.2 all the way back. So that would be this one. And the area between is going to be the larger minus the smaller. So the answer to 3 decimal places would be 0.414. Now you can also do this with the z-table. If you convert 51.2 to a z-score of negative 0.48, we'll find this left area in the table, the negative z-score table. We look up the probability, or I meant to say the z-score negative 0.48. So I'm going to look for the column that starts with 0 all the way to the left, and then 0.48, so it's 0.4 here in this row, lined up with 8 as the last digit in this column. So you can see that I found that same area using my z-score table. I can do the same thing for this area using this z-score of positive 0.61. So looking up the probability in the positive z-score table for 0.61. Here it is, 0.6, and then 1 is the last decimal, 0.7291. Oh, that looks different than this. Is it 0.61? Let's look it up again. 0.61. Why is that different? 0.7291. Mean of 0, standard deviation 1. When it's standard normal with z-scores, you always use 0 and 1 for the mean. True for cumulative. That's the right answer there, so maybe something went wrong in my calculation over here, but I did get the right answer. So that's interesting. Let's just do it again to make sure. Oh, I know, because the mean, when you're doing it with non-standard values, sometimes you will get a slightly different probability. Now, if I do the same thing again with the z-score, with a mean of 0 and a standard deviation of 1 for cumulative. Oh, that's still different than what I had. Must be because this is not rounded to 2 decimal places. If I show this to more decimal places, let's go to, you can see that it's a little different there. So that's the explanation for why there's a slight difference in the probabilities, but it's close enough that it works.